Hello everyone, welcome to my presentation. Today I'm going to present the topic of automatic data extraction based on semiconductor datasheets for design automation of power converters. My name is Fanghao Tian. I'm a PhD student in Leuven, Belgium. In this presentation, I will start with a brief introduction about design automation of power converters. And then I will explain the detailed procedures for data extraction from semiconductor datasheet, including the task overview, the CenterNet, which is the object detection algorithm we used, and also the 9 data extraction details. After that, an improved power loss calculation model for transistors is introduced by using the dynamic data extracted from datasheets. Then the next part is simulation results, and the final part is the conclusion. I'll start with the introduction. Nowadays, new energy technology is becoming a critical research topic. For example, electric cars, solar photovoltaic system, and wind power system. In the meantime, power converter plays an essential part for those emerging energy technologies. For example, in electric cars, power converter is needed for battery charger. And in PV panels, the PV inverter is needed to transfer the DC power to AC power. As you can see, power converters are widely used in all kinds of new energy technologies. So we can see that power converter is one of the enabler to new energy technology. However, in the other side, the new energy technologies gives more strict requirements on power converter design, especially for its efficiency, for its volume, or for its mass. But in the meantime, in the power converter design, there are many factors that affect converter performance, such as circuit topologies design, the magnetic module design, and also the choices of semiconductors and other components. All those factors make design itself a complex activity, because combining each possible design of magnetics and each choices of components can result in a large amount of possible designs. With thousands of possible designs, in order to define the optimal one, the computation becomes extremely expensive and also time-consuming. However, nowadays, artificial intelligence has been developing rapidly, and it has the potential to deal with the complex design problems, and it can speed up the overall power converter design process. That is why the topic of design automation of power electronics is drawing people's attention. As the essential component in power converters, semiconductor component is one of the main factors that cause power losses. So, in the power electronics design process, the selection of semiconductor components significantly impacts the performance of power converters. Traditionally, engineers tend to choose the components based on their experience, because it's impractical to manually inspect thousands of semiconductor components. And also, the market is filled up with semiconductor switching devices with similar voltage and with similar current characteristics. As a result, additional time is spent on selecting a proper device. So, that's why the pre-simulations are necessary for selecting the proper components. The traditional way of calculating the power losses on semiconductor components are based on a simplified model with constant parameters. However, most of the parameters of semiconductor components are actually dynamic. For example, in transistors, the drain-to-source resistance is changing by the gate voltage, drain-to-source current, and even the temperature. So, by taking account in all of the dynamic characteristics, we can get a more accurate semiconductor loss calculation model, which will benefit the power converter design automation. But for realizing that, how can we get the dynamic data for semiconductor components? The answer is that we have to extract them from manufacturers' datasheets. As is shown in the picture, the datasheets have several features. Firstly, there are intensive figures on some pages. Secondly, some figures are in grayscale, while some figures are in color. And also, the figures are almost all line charts and usually have grids. So our work focuses on how to extract the dynamic data from datasheets automatically. More specifically, we focus on creating an artificial intelligence-based tool to extract the dynamic data from line charts of semiconductor datasheets, to develop a method to improve semiconductors' power loss calculation modeling for simulation in power converter design automation. Well, next, I will introduce more details about how to extract data from semiconductors datasheets. To automatically do the data extraction from datasheets, there are two tasks to finish. Firstly, figures in the original datasheet should be detected and cut off. Secondly, dynamic information data should be extracted. More specifically, three steps are needed for task 2, which are object detection, the text recognition, and line data extraction. For the object detection step, the key elements in figures should be detected, such as title, legend, labels, mark values, corner, and others. After this, text in title, legends, and also the numbers in mark values are recognized. Then, with the information, finally the lines are extracted, and finally the data are obtained with the coordinated information. For both tasks, object detection is an essential procedure. Here, a convolutional neural network-based object detection algorithm is used, which is called CenterNet. CenterNet is a new anchor-free object detection algorithm with good performance. The structure of CenterNet is shown here. With the input figure of dimensions of 512 multiply 512 and multiply 3, the ResNet 50 is chosen as the backbone neural network for feature extraction. After this, a feature map with dimensions of 16 multiply 16 multiply 2048 is obtained. Then, after 3 times transposed convolution, we get a high-resolution feature map. By analyzing this high-resolution feature map, the categories of object is determined by the center heat map. And then the specific center position and the width and length of the object can also be obtained. For training the CenterNet, images need to be annotated to form the training dataset. In task 1, let's call it figure separation task, the positions of figures need to be detected. So pages of transistor datasheets are collected to construct the dataset for training. In those training datasets, all individual figures are annotated. An example of the annotated page is shown here. For task 2, let's call it data extraction task. The training data here are all individual line charts. Differently, 6 different key elements are annotated in this picture, which are title, legend, label, mark value, corner, and the others. By recognizing title, legends, and labels, the main functions of the figures are determined. And all those information can be extracted by optical character recognition algorithm, which is also called OCR algorithm. With all those information, finally, the last step is to extract the data lines in figures. Before digitalizing data from a line chart, it is necessary to specify the coordinate information. To do that, I need to binarize the figure and delete the title, legends, and label area. And then I will detect the vertical and horizontal lines and align them to the mark values. By the way, the mark values are obtained by OCR as well. Once the coordinate information is determined, we use the morphologic image processing algorithms to remove everything except the line part. Here, as you can see, only the scatter length of the data line is kept. That means the width of each line is only 1 pixel. However, for some line charts, multiple lines are in the same figure, and the lines can cross each other, like the one in the picture. For those situations, an additional step of data correlation is required. For all points collected from the scatter length, one point position can be predicted by the previous two successive points, by the equation shown here. Then, among all those points, the closest point to the predicted point is regarded as in the same line with the previous 2 points. Then, the next part. With the data extracted from the datasheet, how can we improve the power loss calculation model or transistor? In this section, I will give some brief examples. Here, a detailed internal transistor model is shown here, with indicating intrinsic capacitance. The traditional way of a power loss calculation model with constant parameters, including 4 parts. The first part is conduction loss, which is caused mainly by the drain-to-source resistance when the transistor is on. The second part is the gate loss, which is mainly caused by the energy required for charging the input capacitance. The next part is switching loss, which is highly relative to rising and falling time. And finally, the last part is reverse recovery loss, which is related to the output capacitance. However, according to the datasheets, most of the parameters for calculating the power loss in the previous slides are dynamic. For example, for the conduction loss, the conduction resistance is actually a variable that is dependent on the junction temperature and the drain-to-source current. So, a dynamic conduction loss map should be used by considering different values for resistance in different conditions. Then, for reverse recovery loss, the output capacitance is a variable depending on drain-to-source voltage. So, instead of taking output capacitance as a constant, an improved calculation method is shown in the equations below. The original equation can be replaced by an integration function. So, in this way, the traditional calculation model for power loss of transistors can be improved. The next part is simulation results. Here I will show the training losses for the object detection algorithms and examples of detection results. The datasets are divided into training dataset and validation dataset. The results show that the training loss reduced dramatically and stays at a small value. The final training loss are 2.59 and 0.78 for both tasks, and the validation losses are 2.15 and 0.57 respectively. With the small training and validation losses, the trained CenterNet can detect the key elements from a datasheet page or from a line chart. The example of result for task 1 is shown here. As you can see, every figure on this page is detected and selected by the red bounding boxes. With the bounding box information, those figures can be cut into individual figures. And all those individual figures can be recognized by the task 2. Then for the line chart data extraction task, as you can see here, the key elements are highlighted by bounding boxes as well, but they are also classified according to the predefined classes, such as the title, the legend, the label, mark value, corner. Well, once we have the results, after applying the OCR for text recognition and also the image processing algorithms for the line extraction, then the dynamic data are extracted from the datasheets successfully. Finally, the last part is the conclusion. Power loss simulation is critical for design automation of power electronics, and they usually have unavoidable power losses, especially at high frequencies. As a result, an accurate calculation model of semiconductor power losses can result in the optimal selection of a specific components for a specific power converter design. By acquiring dynamic data from datasheet, it can help improve the calculation model of power loss. So, in this paper, a CenterNet-based tool, especially for data extraction of semiconductors datasheets, is proposed. Firstly, CenterNet was trained for 2 tasks, which are figure separation from the original datasheet and also the key elements recognition from the line charts. Secondly, the final data extractions is accomplished by using the image processing techniques. And then, finally, an improved dynamic power loss model by using the dynamic data extracted from the datasheets is explained. So that's all on my presentation today. Thanks very much for your attention. If you have any comments or questions, please contact me, and thank you.